Hi, everybody. I'm going to talk about the Mediterranean environmental rearrangement for the Miocene in light of variation in oceanic gateway connectivity. And let me start with that, assuming that I can get the screen to move. Okay, so let's start with oceanic gateways. Oceanic gateways are relatively small regions where water are exchanged between oceanic basins. Think about the Straits of Gibraltar or the Bab el-Mandeb or Straits of Hormuz. And the opening and closure of these gateways have a dramatic effect on oceanic heat and salt distribution, both in the smaller basins that they restrict and in the larger ocean itself. One of these, the most dramatic probably cases for this would be the opening of the Drake Passage. But overall, over the Cenozoic, we're seeing a lot of these gateways opening and closing. And as they're doing this, they're rerouting the way that thermal regulation of the planet works. So one of the things we're seeing through the Cenozoic is this shift from low latitude oceanic gateways to high latitude oceanic gateways. And as that goes in, that plays a major role in the greenhouse to icehouse transition. So in today's talk, I'm going to talk about two things. I'm going to talk about the Mesopotamian gateway and its termination, and how does that impact the sedimentary system in the Mediterranean, where I'm going to talk specifically about carbonate sedimentation. And my talk will be focused actually on two places. It's going to be on Cyprus and on Malta. So let's start with the depth of the bays. The Tethyan Ocean, or at least the Neo-Tethyan Ocean, started around 255 million years ago and lasted around 10 to 20 million years ago, depending on how you define that. And it was a major ocean surrounded by most of the Earth's continental mass. But more importantly, as of around 160 million years ago, it was the principal conduit of the oceanic meridional circulation. That means the current that went around the planet through the low latitudes. By the late Oligocene, all that was left of this major ocean and this major current was the Mediterranean basin and a narrow seaway, which we call the Mesopotamian Gateway. And that was connecting the Mediterranean and the Indian Ocean, but that was also what allowed water to come around all the way from the Pacific, through the Indonesian through flow, up into the Mediterranean, down into the Atlantic, through the Panama Isthmus and back to the Pacific. And we have some sense of this connectivity about how things related to one another, but a lot of this came from macrofauna, onshore and offshore, like this Gonotherium land bridge, so this land mammal transition from Eurasia to Africa, or transition of the speciations of the mollusks. And that was good, but it was kind of broad stroke because the zonations are very big and there was a lot of guesswork going into that. And the closure had multiple drivers and mechanisms going into it. We had compression due to the northern migration of Africa. We had inner plate volcanism that formed islands in this seaway. And those are important, we'll get to that later. And also flexural and thermal doming in the area south of the Zagros. So we have a lot of things going on. So it's not like you can say, oh, these two land masses touched, it's over. There's a lot of things going on. How could we refine this to get a timeline of the events? So the way I elected to go about this was to use neodymium isotopes. Neodymium isotopes, we know a lot from the tidal work, provenance, and that sort of stuff. But we also have another type of application. We can use it for pathogenic minerals forming, especially in water. So while the detrital aspects allow us to look at provenance, the orthogenic allows us to trace water mass. Problem is, this detrital signal kind of overprints. So the way to go around this, the way to get signal that represents the water mass is to go as far away from the content as possible. But if I want to trace a surface current, that's a bit more difficult. And the way to go around this was to go to isolated carbonate platforms. These are regions far removed from the continents, sitting in relatively shallow water, and they are a good way to get the marine signal of the surface and subsurface waters. So we have two of these. One of them being Malta. That was an isolated Mediterranean carbonate platform that persisted through the Eocene all the way to the Miocene, all the way to the modern to some respect. And the other one was site U1467 in the Maldives, which gave us the baseline for the Indian Ocean. But to get like a sense of what this would look like, the first stage was to do some modeling. So this is the schematic diagram of a box mold for the Mediterranean with influxes and outfluxes for the modern. So we have about 0.78 sphere drops coming from the Atlantic, 0.71 sphere drops going out as the Mediterranean intermediate waters, about 0.3 sphere drops coming from the Aegean and Black Sea, and lost towards evaporation. And that gives a signal, an epsilon neodymium signal about -6.6. Now, let's plug values for the early Miocene, late Oligocene. So the Atlantic is much better connected. That gives 4.8 sphere drops, 5 sphere drops. The Perithetis is also much bigger. It gives us also a lot more water, about 1.2. And the Indian Ocean is giving us 22. So, that means that, so the amount of water that used to be coming in from the Indian Ocean compared to what we're getting from the Atlantic now was over 20 times larger. So we plug those values in. The Indian Ocean had a value of about -8 that we validated from the work in the Maldives. And that means that the Mediterranean neodymium isotope values should have been lower. But then we went out and actually did measurements. So in the so these are the epsilon neodymium curves versus time for the Indian Ocean in blue, in the upper column for the Maldives, below that for the Mascarene Plateau, that's intermediate waters, underneath that Malta, and underneath in northern Italy, which is a more composite signal because that also sees what's coming out of the Perithetis. And each of these bars are indications we have of like events going on. And we know that in the late Oligocene, the connection should still have been open. But what we're seeing from the neodymium isotopes is very radiogenic values. So what's going on? So here in Malta, you can see that, but we also see this in Italy. So you go back to the map, you go like, okay, what's going on here? And then, remember those volcanic islands I talked about? There was a lot of them. There was a lot of back arc volcanism going on. We also had the Domingan Afar and proto-Hellenic volcanisms around Anatolia. So that's a lot of alkaline igneous provinces all over these conduits. And once we factor in the erosion of this alkaline material, it's possible to trace more or less the changes, because all around this conduit of the Mesopotamian gateway, we had all this volcanism and all this volcanic igneous and all this alkaline igneous material. And when the connection was open, all of that was eroding and flowing into the Mesopotamian gateway. And with all these waters coming from the Indian Ocean, they were enriching the water with radiogenic overprint. So that gives us the signal for the earliest Miocene and the late Oligocene. But once we say, okay, these are more or less the erosion factor, we can use that to actually calculate how much water we had coming in during the early Miocene, which we think was around 20 sphere drops, and based on that, calculate how much we could have had by the late Bertigalian, like by the middle Miocene, and that decreases about 90%. So around 20 million years ago, we see a 90% decrease in the amount of water coming from the Indian Ocean. And that amount continued to decrease until it dropped very abruptly around 14 million years ago. So that gives us three main stages: an open stage until around 20 million, a restricted phase until around 14, and then a closed stage. That was where we were in 2019. But then there was new work that was done in the Levitt Basin by Adi Torpstein and Josh Steinberg, and that gave us another set of constraints. So this is data coming from the deep basin, and there's already indication of closure between 21 and 24 million years. So that gives us another point in our timeline. So this is how our timeline would look now. We have our initial restriction phase, which we are calling MRS0 now. And in that stage, it's probably the loss of connectivity of deep water. Then that's ends around 21. Then we get MRS1 around 20 to 19. And then we lose 90% of the surface connectivity. And what we're left is this intermediate, irregular, restricted connectivity, which lasts around until 13, 14, we get to MRS2, and after that, we lose connectivity completely. The nice thing is that each of these phases also comes along with other things that we're seeing, like a Mesopotamian evaporite emplacement, movement along, some indications for movement along the Dead Sea Transform. This Ganophorium land bridge falls very nicely within that. And also things that we're seeing in the Indian Ocean, like the beginning of upwelling in the Arabian Sea, which is a story in its own right. So we have our timeline. So now that we know when things are happening, we can start looking at what they're doing. So we had this nice low latitude circumglobal current, and it's diminishing until it's gone. And the Mediterranean goes from this seaway connecting all the world's ocean into a more and more restricted basin. And well, when you do that, there's a huge shift in the way circulation works. So this is a modeling work that was done a couple of years ago, showing how circulation in the Mediterranean would have worked. So surface waters would come in from the Indian Ocean, they would go to the west, then they would sink down and come back into the Indian Ocean, forming what used to be called the Tethyan intermediate waters. When we close that gateway, things change. So now deep water circulation becomes a lot weaker, and surface circulation just completely changes. Instead of coming from the east, it's now coming from the west, and it goes out to the west. So that's a very fundamental shift in the way the Mediterranean was functioned. Currents were going, and where they were coming, what they were going, what were their directions, and that leads to a reorganization. But this is a big process. The Mediterranean has seen a significant shift in the way its carbonate factories were working. So this is a new compilation we just submitted of carbonate production in the Middle East. And through the Cenozoic, we can see that we're starting in the Paleogene and Eocene. We have a lot more photozoan production, going all the way to the Oligocene, and then suddenly, as we hit the Miocene, photozoan production crashes, heterozoan production goes up, and also production of non-skeletal grains goes up. So the entire mode of carbonate production in the Miocene, and most of this change occurs as of the late Bertigalian, shifts. Let's take a second and look at what was before. This is a 3D model that I made for one of the outcrops of the Lower Coralline Limestone. It's what we have here is a cliff in a place called Arlapsi. And if we do a bit of interpretation, we can see it's a very big carbonate platform. It's about almost 90 meters tall. It has multiple production centers that interplays. It responds to sea level, and its production rates are very, very high. But then around 25, 24 million years ago, which kind of sounds familiar now, it goes from being this nice carbonate factory with corals and coralline algae, and it rapidly dies out. So we go from this, from the corals and corallines to this more sandy stuff, and then that gets replaced by echinoderms dominated, and then it completely drowns, and we go into this pelagic phases, and then eventually at 24, there's a hard ground, a phosphatic hard ground. Something shifted, something significantly shifted. Here's Cyprus, Greco, again, big carbonate platform, very wide, corals, coralline algae, lots of stuff going on, but we're losing that into the middle Miocene. But the problem is with these shallow water carbonates is they're very hard to date. We have only large benthic foraminifera. They're not very well preserved. There's a lot of recrystallization. So if we want to get like at a good record, we have to go from these shallow waters into the deeper waters. So we went to Cyprus, and we found a section. And with the tectonics in Cyprus, it's tricky, but we managed to find a section, build it back into the shape, and generate a record from around the 21 to 16 million years in that area. And this is on the slope. So what this columnar section shows is textures, the carbon isotope, the carbon content, shallow water components, pelagic components, and then in the brown, phosphate. The big blue triangles indicate bottom current dominated sedimentation. Green are mass transport dominated sedimentation, and the gray bar indicates how much pelagic we have. And the bottom, you can see we have this nice triangle, this nice bar of shallow water components, and then it gets dominated by pelagic stuff, and then phosphate comes in, and we lose the supply from the shallow water, and we're losing the supply from the shallow water because something happens to that production. If we look at this more closely, here's the lower interval with a lot of material getting transported from the shallow water, from reefs. We have entire coral being transported as mass transport deposits, large benthic foraminifera and fine grain. This stuff, the slope here sees a lot of material getting reworked from the shallow water carbonate factory. As we go further up, we lose these shallow water components. Something happened to them. And if I jump over to Malta for a second, as that happens, we see this transition from relatively low sedimentation rates into very high sedimentation rates. So we get an entire shift around 20 to 19 in how production works. This shift towards more pelagic production and loss of shallow water production. And by the time we get to the middle Miocene, we're in a completely pelagic realm in southern Cyprus, we're in a completely pelagic realm in Malta, and we're also seeing a lot of phosphate. But not only phosphate, we're seeing something else. We're seeing the initiation of sapropels. This is from Cyprus again. We see this mostly. We have these nice pelagic records in northern Cyprus, where we're seeing these sapropels starting around the same time. So what this indicates is that we have a shift both in the freshwater balance, but also in the nutrient regime in the Mediterranean. This is not this nice tropical waters that we used to get. These are more restricted basins, very strong salinity oscillation if we are getting sapropel, but also strong nutrient pulses going back and forth. To understand how one thing relates to the other, we need to go to the Atlantic first. This big red blob that you see here, marked MOW, that's Mediterranean outflow waters. These are waters that are coming now from the Mediterranean into the Atlantic Ocean. Before the closure of connection to the Indian Ocean, these were the Tethyan intermediate waters. They would go to the Indian. Now, as of the middle Miocene, they're going into the Atlantic. And if you look at this in a reconstruction of the intermediate waters, so to the left, early Miocene, they go to the Indian Ocean. On the right, middle Miocene, they're going into the Atlantic. And as they're going into the Atlantic, they invigorate the Atlantic meridional oscillation, the AMOC. And as you invigorate the AMOC, we know that is correlated directly to precipitation in North Africa and in Europe. So we're getting more fresh water, which is probably what's triggering these sapropels, and also oscillates what's going on with the nutrients. Now also, we need to factor in that the shift in intermediate waters from going to the east to going to the west also possibly was generating upwelling in certain areas. And that upwelling probably played a role in all of this phosphate that we're seeing around that. And we're seeing quite a bit of phosphates. This is data from the Sicily channel, mostly based on the Maltese section. And we have a lot of phosphate suddenly starting in the early Miocene, and then tapering out until they're gone around the same time the sapropel starts. So we're seeing this very fundamental shift in the way nutrients are being organized in the Mediterranean. And as the sapropel starts, we're getting the first stochastic unit in Malta in 100 million years. So we're getting a lot of water suddenly coming into Africa. And if we look at the phosphates, which are these black bars in the middle, we map them out in the central Mediterranean. So in the early Miocene to middle Miocene, we have them in Malta. Then they shift to Sicily. Then they shift to Salento. Then they shift to Matthias. And in Mayella, we used to think that they were starting very further late, but now there's new data that shows that they're actually orbitally punctuated, but still a northern migration. And in that, Cyprus also starts seeing these phosphates more or less at the same time we're seeing them in Sicily, which is about the same latitude back then. And all of this is happening during the restricted phase. Once we get into the closed phase, we don't have the phosphates in the lower latitudes, they're going further up. But this nutrient rearrangement also, again, comes along with the termination of the shallow water production. This is nothing new. This is something we've been there already pointed out in the 90s, working on the Eastern Mediterranean. And he was seeing this in Israel, he was seeing this in Lebanon, he was seeing this in Cyprus, in Turkey, and we can add to that Malta and Sardinia. The middle Miocene has a reef gap. We don't have reefs for some reason. And there are some things in Italy, but they're not really platforms and reefs. They're more of these shallow slope, these nice ramps. But there is one place where there's continuation. And I'll get to that in a second. But let me talk about what came after this reef gap. So these are the reefs in Cyprus after the gap. They're a lot smaller than what we had before. They're a lot more influenced by local uplift, and the factories are very different. But south of Cyprus, we have the only site where we have shallow water carbonate production through the entire Miocene, and that's the Eratosthenes Seamount, which was drilled by ODP back in the 90s. And my collaborator Giovanni Coletti in 2019 did a reevaluation of the carbonate faces and factories. So we have a good description of what was going on there. And you can see there's a big difference between the early Miocene, middle Miocene, and late Miocene there. But that's just one site, and that doesn't give us enough data. Luckily, the German Geological Survey did some seismic work there, so we can also look into the seamount and map out their productions. And we can, and thanks to new data that came from the Levant Basin, we can build a stratigraphy coming from the east to the west and tease out the ages, and then map out the production modes. So we know that in the early Miocene, we had a proper carbonate platform there. But as we're getting to the middle Miocene, the base of it delineated by the bright blue line here, we're going into these weird meandering clinoformal bodies. And then as we go into the late Miocene with the dark blue line, they're gone and we're getting proper platforms. And we have similar seismic cases. So we know these clinoforms, they're grain-dominated production. So mostly coralline algae, bryozoans, bivalves maybe. These are not corals. So we're going from these nice platforms, nice reefs and carbonate factories of the early Miocene. And with the restriction and this nutrient rearrangement, we're losing all of them. We're getting something that's dominated by algae, by bryozoans, kind of like what we have on the Israeli margin today. And then in the late Miocene, reefs reassert themselves. But they're not the same. They're smaller. If we compare them, the early Miocene reefs were mostly mesophotic. They were larger platforms. They had corals across multiple locations. They had a lot more productions by echinoderms, large benthic foraminifera. But in the late Miocene, they're mostly photic. They're a lot smaller and narrower. All the corals went up, and the corallines got pushed to deeper waters, and we lose a lot of the other carbonate producers that we had there. The conditions are different, and they don't like it anymore. But I want to stop and think for a second on the other side. So we know what's going on in the east. We lose the connectivity that happens somewhere, that happens between 24 and 14 and multiple steps. But that's gone. By the middle Miocene, that's gone. We still have connection to the east. On the other side, we're still connected to the Atlantic. Well, part of it. It's not as good as it used to. So this is a compilation I made from data from the Eastern Mediterranean, Central Mediterranean. And in the upper part, you can see strontium isotope data. The nice dark line, that's the oceanic compilation. That's the values from there. But the values coming from the Central and Eastern Mediterranean started to depart out. We're starting to see a lot more restriction of the Eastern Basin as early as 8.5, maybe 9 million years ago. And part of what's driving that is the uplift of the Maltese barrier, this high underneath the Sicily Channel that separates the Eastern from the Western Basin. So we have an increase in restriction of the Mediterranean. And the nice thing is just there was a new paper that just came out of Crete showing this significant increase in salinity in the Eastern Basin, going to values 40, 44, 47. This is higher than we have in the Red Sea. So the Eastern Mediterranean was very restricted. And these very high salinity waters were getting pumped back into the Western Mediterranean, giving us conditions that are not, let's say, more complicated and maybe less hospitable for certain groups. And this is happening many millions of years before we lose connectivity, full connectivity with the Atlantic Ocean. But we might already be starting, because the next point, we kind of know where it's going. But while this is restricted, that already starts forming as a gradient. So these are carbonate platforms from across the Mediterranean, going from Spain at the top to Malta to Cyprus. And you can see the difference in sizes and in character. And it's also in characters. In Spain, we have a lot more green algae, we have corals. In Malta, not so many corals. By the time we get to Cyprus, it's mostly coral and algae. And where we have corals, it's in very, very narrow range. So we have a gradient across the Mediterranean, at least until the Atlantic connectivity goes out completely. And then all that's left is salt. And all the biology and everything that will come after this is a completely different world. It's a world that is dominated by Atlantic fauna, because everything that was Tethyan just died out. So let me wrap it up. Surface exchange across the last vestige of the Tethyan seaway into the Mediterranean terminated in 3 phases during the early and middle Miocene. Around 20, we'll see a diminishing of 9% of surface exchange, and by 14, we lose it completely. The loss of this connectivity, it does a real number on the habitats of the Mediterranean. It reshapes Mediterranean outflow. That in turn shifts how climate behaves in Western Europe, in North Africa, and that turns the Mediterranean from this very open ocean to this very restricted ocean with strong salinity oscillation, a strong nutrient oscillation. It kills off, or effectively kills off, the reefs. And by the time they reassert themselves, they're not what they used to be. They're a lot smaller. They're not as significant. And then everything just dies out. It's kind of a tragedy. Yeah, and when we try to think about these poor platforms. Okay, and some acknowledgements. There are a lot of money from different sources came to this work. It was funded by the German-Israeli Fund, by the GIF, by Cost Action, by the European Consortium in IODP, by the Israeli Mediterranean Research Center, and of course by my Marie Curie, with multiple collaborators across Europe. And with that, I'm going to call it. I will make the note that this is the story on the Mediterranean side. There is an entire separate story about what this is doing to the Indian Ocean, but that's a story for another day. Thank you for your attention.